Now we are on section 6.3, the development of quantum theory. Here we're going to extend the concept of wave-particle duality that was observed in electromagnetic radiation to matter as well. Understand the general idea of the quantum mechanical description of electrons in an atom, and that it uses the notion of three-dimensional wave functions, or orbitals, that define the distribution of probability to find an electron in a particular part of space, and list and describe traits of the four quantum numbers that form the basis for completely specifying the state of an electron in an atom. So this is the last section for this week. Next week we will go over section 6.4 and 6.5. This section is probably the most difficult because it's so different. Even section 6.1 and 6.2, they are different, but at the very least we're dealing with equations. Here is very conceptual, and it's not something you can really picture very well. So let's talk about the development of quantum theory. Particles and waves in the macroscopic world are really different, right? A wave in water is a lot different than a fish in water. But by the 1920s, it really was becoming more and more clear that really tiny pieces of matter have really different rules from what we see with large objects. So we could no longer say that waves and particles are completely different for this microscopic world. This is just an example of interference patterns on a water surface. So you can see where the waves from these, where these waves of water interact, you can actually see areas where they combine and where there's little nodes. So Louis de Broglie came up with this question. If electromagnetic radiation can have particle-like behavior, can electrons and other submicroscopic particles also exhibit this wave-like character? So he took the wave-particle duality of light from Einstein to material particles in 1925. And we have the de Broglie wavelength from him. And this is characteristic of particles, not electromagnetic radiation, so not light. Particles. And what's kind of crazy is he did this in his doctoral dissertation. And it really puts my dissertation work to shame. So this lambda here, this de Broglie wavelength, is characteristic of particles. And again, not light, not electromagnetic radiation. And here we're also using velocity, not frequency. Okay? This should be an actual V for velocity. It shouldn't be nu anymore. It should just be V for velocity. So this de Broglie wavelength is equal to Planck's constant divided by mass times velocity of the particle, which is equal to Planck's constant divided by the particle's momentum. So Bohr came up with the idea of the electron being a particle orbiting the nucleus with these quantized orbits. But de Broglie took this assumption and explained it by considering the electron as a circular standing wave. Okay, and so only an integer number of wavelengths could actually fit within this orbit. So by using this, okay, here's an example of it. And you can see where the wavelength is. By using this assumption, an integer number of wavelengths can fit into an orbit for the standing wave in order for this to be possible. So then we have now a circular orbit with this radius of r. just like a circle has a circumference of 2 pi r. So his condition is that the circumference is equal to n of our orbit times the wavelength. And then we come to scientists at Bell Laboratories, C.J. Davison and L.H. Geramer, and they were able to show experimentally that electrons can exhibit wave-like behavior by showing electrons going through, giving this atomic pattern in a crystal, making an interference pattern. And that this interference pattern is very similar to that of light. So here's an example. The top picture shows electrons going through double splits, just like was done with light. And it shows this wave-like behavior of these bright spots and these dark nodes. And then in B is also showing this wave-particle duality of electrons. The more electrons that are going through this double split over time go from looking like just kind of little particles. As we add more and more, we start to see over time it looks more and more like a wave. So these aren't 3 sheets in front of each other. This is time passing and more electrons being allowed to pass through the double splits. So you can see the wave-particle duality. So even though electrons are these small particles, their motion does not follow classical mechanics. They have some type of wave equation that has this distribution, this probability distribution for its motion. So this wave-particle duality of electrons that we first looked at with photons is intrinsic to all quantum particles. It's not just photons. Electrons also, all of our quantum particles. Before we go here, I want to look at a quick example. We're told an electron is traveling at a velocity of 1.000 times 10 to the 7th meters per second. Meter second inverse, okay, that's the same thing as meters over seconds, and has a mass of 9.109 times 10 to the negative 28 grams, and we want to know the wavelength. So we're going to be using de Broglie's equation, but we first need to do a quick little conversion, remembering that 1 joule is equal to 1 kilogram meter squared per second squared. So if we take Planck's constant, h equals 6.626, I don't know why I always try to do 6.626 times 10 to the negative 34th joule seconds. Okay, we can rewrite those units because we know that 1 joule is 1 kilogram meter squared second squared. So now that becomes kilogram meter squared per second squared times seconds. One of those seconds cancel out. So now it's 6.626 times 10 to the negative 4th kilogram meter squared over seconds. Okay, so this is specific just to get our units where we need them. So then from the de Broglie equation, we know that lambda is equal to h over mv. And so we're going to go ahead and plug and chug 6.626 times 10 to the negative 34th kilogram meter squared over seconds. This is also how this equation works, so it's nice to show you that. times our mass, 9.109 times 10 to the negative 28th grams times, oops. Oh yeah, and we also need to change our grams to kilograms. So we can just put that conversion down here, times 1 kilogram per 1,000 grams. Times our velocity of 1.000 times 10 to the 7th meters per second. Oops, I'm running out of room. Meters per second. So kilograms here cancel, seconds cancel, and then one of our meters cancels, leaving us with 1 meter, which is what we need. So this is 7.274 times 10 to the negative 11th meters. So that is the de Broglie wavelength of the electron. All right, so that brings us to Heisenberg. No, not Breaking Bad. So Werner Heisenberg determined that there's a limit to how accurately we can measure a particle's position and its momentum at the same time. The more accurate we measure one, the less accurate we are with the other. So this is the Heisenberg uncertainty principle. It's fundamentally impossible to determine at the same time, simultaneously, and exactly both the momentum and position of a particle. So this is the equation. Delta x, which is the change or the uncertainty in the position of the particle, times delta px, which is the uncertainty in the momentum of the particle in its direction, is greater than or equal to h bar. And h bar here is equal to Planck's constant of h divided by 2 pi, equal to h bar over 2. Let me go back. So for instance, let's say that we improve our measurement so that the uncertainty in position of delta x is 1 picometer. Picometer, so cute, which is 10 to the negative 12th meters. Okay, and so then we can solve for delta p, divide both sides by delta x. So delta p, which is the same thing as saying the mass times our uncertainty and its velocity, is equal to h over 2 pi for h bar divided by delta x. Oh, sorry, let me just h over 2 divided by that. And we plug everything in and we get 5 times 10 to the negative 23rd kilogram meters per second. So this uncertainty, we really can't see it for something like a baseball. But for something like an electron, it can be a very, very big uncertainty. All right, so then we move on to Schrodinger. Schrodinger took de Broglie's work and incorporated the de Broglie relation into a wave equation, and this is called the Schrodinger equation. And he thought properly that the electron in terms of a three-dimensional stationary wave called a wave function, which we represent with the Greek letter psi, which is that thing there. From there, Max Born was able to say that electrons are still particles, so the waves represented by psi are not physical waves, but are probability amplitudes. Okay, so they can be in different places, and they can have peaks and troughs. The square of its magnitude describes the probability of a quantum particle being present near a certain location in space. Just means that you take the square of it, and that tells you how likely it is to be in a set spot. And we can use these wave functions to determine the distribution of an electron's density with respect to the nucleus. So we can say, okay, I'm using this wave function, and I can say that this area is the most likely area that this electron can be found. So the Schrodinger equation can be written like this. The Hamiltonian operator is equal to the wave function of the particle times the energy. And the wave functions are super complicated and crazy. So don't worry too much about this, okay? Don't let this scare you. There's not going to be test questions on trying to solve the wave function. But this work of Schrodinger combined with Heisenberg and so many other scientists is called quantum mechanics. So we're going to talk a bit about quantum theory as we go along in this section. But first, a joke that I'm sure you've heard before. Heisenberg and Schrodinger are speeding along the freeway, and they get pulled over. And the police officer comes and gets them to roll down the window, and he asks them, "Do you know how fast you were going?" To which Heisenberg looks at him and goes, "No, but I can tell you where I was." The police officer finds this kind of suspicious, so he makes them pop the trunk, and he looks back there, and there's a cat back there meowing at him. Yes, I've changed this a little bit. And he goes back and goes, "There's a cat in your trunk. Did you know there's a live cat in your trunk?" And Schrodinger looks at him and goes, "No, but I do now." No, we haven't talked about Schrodinger's cat, but still. Heisenberg and Schrodinger. There you go. Moving on. Quantum mechanics. So let's try to understand quantum theory. So yeah, now you guys can go tell your friends, I'm studying quantum theory. And it's really not as bad as it sounds, at least at our level. When you get on to PChem and if you go into engineering and whatnot, it gets worse from there. But it's pretty cool stuff, I'll be honest. So we know that electrons can exist only in these discrete energy levels, but not between them. So you can't have a 1.5 energy level. The energy of the electron in an atom is quantized. Okay? The energy is only specific values. We can jump from one energy level to another, but there's no like smooth transition of it going from, oh, I'm going to go to 1 to 2 to 3. No, it goes from 1 straight to 3. Okay. But that transistor smoothly. And it can't stay in between levels. We can't have it chilling at level 2.5. There is no level 2.5. Kind of like books on a shelf. Okay, you can't have a book in between shelves. So the energy levels, we've seen this N number, and we're going to continue on with it. And this is representing the energy levels. So N can be 1, 2, 3, and so on and so forth. The higher the N, the higher the energy associated with it, of the electron. So we call this the principal quantum number, or the shell number. Okay, and this tells us the location of our energy level. Similar kind of in concept to our Bohr model of the atom and the electron. So these different shells are numbered by principal quantum numbers. So we can kind of think of this as the shells of an atom. Think of them as circles radiating out from the nucleus. The further we get from the nucleus, the higher the shell number, the higher the energy. And the reason this is because the closer we are to the nucleus, the closer the electron is to the protons of that positively charged proton, which are going to stabilize the electrons and lower the energy. Remember, lower energy, more stable. So then as we get further along, they're not able to feel that positive charge as much anymore, so higher energy associated with them. So we have three quantum numbers that characterize the orbital. The principal quantum number, or n, is the first. So this gives us the thought of the atomic orbital, and this is a region in an atom that the electron is most probable to be found in. An atomic orbital is different from an orbit. Okay, so the orbit is what we were kind of talking about with the shells. Orbitals are actually three-dimensional spaces around the nucleus. We'll talk about those a little later. But the next quantum number is the angular momentum number, or L. Okay, they do this kind of fancy L. You might just see just L or L. It's L. And this describes the shape of the orbital. So L starts at 0 and goes up to n minus 1. So if you have an orbital of n equals 1, L can only equal 0. Okay, because that's the 1 minus 1 is 0. But if you have an orbital with n equals 2, you can have L equals 0 and L equals 1. If you have orbitals that have the same value of L, you have a subshell. These numbers for L represent letters or types of orbitals. When L is equal to 0, this represents what is called the s orbital. L equals 1 is the p orbital, 2 is the d, and 3 is the f. S, p, d, f orbitals. So that is what these numbers of L represent. I know it feels weird that the numbers represent single letters, but we'll talk about that later. Now, there are certain distances from the nucleus where finding an electron has a probability of 0. The wave function value is 0 at this distance, and this is called a radial node. So we talked about nodes in section 6.1. We have them even in our wave functions for our electrons. The number of nodes is equal to your principal number minus L minus 1. So if you have the 1s orbital, that's n equals 1, L equals 0, the number of nodes, 1 minus 0 minus 1, is 0. There's no nodes for 1s. At the 2s orbital, n is equal to 2, L is still 0, and then minus 1, we have 1 node. The 3s orbital, 3 minus 0 minus 1 equals 2. These are just some examples for you. And this is what this looks like for the 1s, 2s, 3s orbital. So these graphs on the bottom are the probability of finding an electron in these orbitals as a function of the distance from the nucleus. And you can actually see these nodes, these kind of dark spaces. Those are the areas where their probability is 0 as we go up in orbital. Now, these different orbitals, the s, p, d, and f orbitals, have different shapes about them. The s subshell is spherical. Okay, so these are subshells. The p subshell is shaped like a dumbbell, and d and f orbitals are definitely more complex. So we can't just say, oh, they all look like this. And what these shapes represent is the regions where we can find an electron, where they're most likely to be found. So here's what they look like, some of them. So this is the s orbital. They're these nice little spheres. The p orbitals are these dumbbell shapes. So you can see they have a bit of a node too in the middle. And then we have these different d and f orbitals. And they're definitely weird looking. So again, these orbitals represent where an electron is most likely to be found. So if you have an orbital with an angular momentum, so you have L greater than 0, you don't have L equals 0, then this orbital has different directions to it. So this is not the s orbital, but the p, d, and f orbitals. So these have another quantum number called m sub l, the magnetic quantum number, and this tells us the orientation of the orbital in space. What direction is it facing? So the value of m sub l depends on the value of l. It can go anywhere from negative l to positive l. So there are two l plus 1 orbitals within the same l value. If you have one s orbital for l equals 0. When l equals 1, there's 3 p orbitals. So that means there's negative 1, 0, and positive 1. Okay, from negative l to positive l. The d orbital has an l equals 2. So that means we can go negative 2, negative 1, 0, positive 1, and positive 2. The f orbitals, l equals 3, negative 2, negative 1, 0, positive 1, positive 2. Let's say you want to know the total number of orbitals for an atom, okay? Or for an electron. So you're told whatever your n number is, you take the square of it, and that's the total number of orbitals. So let's say n equals 4. Total number of orbitals is 16. Because you're going to have them for each of the s, p, d, and f subshells. So when we're talking about an orbital, we usually give both the n and the letter for L. So we might say 2s, 3p. Okay. In a hydrogen atom, the energies of the orbital, all the orbitals within the same n are the same. This is called a degeneracy. The energy levels with the same principal quantum number, or n, are called degenerate energy levels. But when you have atoms with more than one electron, this degeneracy is eliminated by the interactions between them. Okay, so orbitals with different subshells have different energies. If they're in the same subshell, they are still degenerate with the same energy. So this shows you the different energies of electron orbitals in a multi-electron atom. So we're not just talking about hydrogen anymore. And you can see as we go up in our n, we're going up in energy. And the different orbitals, even at the same n, have different energies also. The 2s is lower in energy than 2p, which is lower than 3s, which is lower than 3p. But we're still going up in energy as we are adding more and more electrons and more orbitals. So NL and M sub L tell us the region of space where an electron is most likely to be located. But there's a different fourth property called electron spin. And this gives us the intrinsic electron rotation. And there's only two quantized states that electrons can spin. Either plus 1/2 or minus 1/2. There's only two possible states. It doesn't matter what orbital it's in. It can only have one of these two values as its spin number. Okay, so it can spin up or spin down. And this is relative to like a magnetic field. Okay, so that's why it's shown north-south, how the electron is spinning. So now we have these four quantum numbers, and here comes Wolfgang Pauli, an Austrian physicist, came up with the Pauli exclusion principle. No two electrons in the same atom can have the same set of all four quantum numbers. They can have the same orbital. They can have the same NL and ML. Okay, and you can also calculate the maximum number of electrons at an energy level is equal to 2n squared. But they can't have all that being the same unless they have different ms, which is that plus 1/2 or minus 1/2 spin. And since there's only two values of spin, we cannot have more than two electrons in the same orbital. if they're in the same orbital, they have to have opposite spins. So one has to be spinning up, the other has to be spinning down. So this table gives you a nice summary of the quantum numbers and their properties. We have our principal quantum number of n, and it can be, 1, 2, 3, 4, etc. And this is the shell, the general region for the value of energy. From there, we have the angular momentum of L, and L starts at 0 and goes up to n minus 1. This is the subshell, or the shape of the orbital. The magnetic quantum number m sub L goes from negative L to positive L, and this is the orientation of the orbital itself. And lastly, the spin quantum number ms, which is plus 1/2 or minus 1/2, and this is the direction of the electron spin. So I have a couple examples to go through because I know this is all kind of weird and hard to understand, so hopefully these examples help a little bit. We want to figure out the number of subshells, the number of orbitals in each subshell, and the values of L and ML for the orbitals and the n equals 4 shell of an atom. So remember that L goes from 0 to n minus 1. So that means that L at n equals 4 is going to be 0, 1, 2, or 3. And so that corresponds to S, P, D, F. Okay? And then ML is equal, we go from negative 1 up to positive 1. So at L equals 0, ML equals 0. For L equals 1, ML equals negative 1, 0, and positive 1. For L equals 2, we have negative 2, negative 1, 0, positive 1, positive 2. And lastly, at M equals 3, or L equals 3, we have negative 3, negative 2, negative 1, 0, positive 1, positive 2, positive 3. Okay, so then we can calculate the number of orbitals. So at ML equals 0, that's 1 orbital. At L equals 1, we have 3 orbitals. At L equals 2, there's 5 orbitals. And at L equals 3, we have 7 orbitals. So in total then, we have 7 plus 5 plus 3 plus 1. We have 16 orbitals in total, which is the same as n equals 4 times squared, which is 16. So you can go and get all of the orbitals manually, especially if you're told to identify what they are with the MLs. Those tell us all the orientations of the orbitals, so that many orientations tells you the number of orbitals. Or you can also do n squared if you just want to know the total number. All right, so here's another example. Calculate the maximum number of electrons that can occupy a shell with A, n equals 2, B, n equals 5, and C, n as a variable. Note you're looking at the orbitals specified with the n value, not those at lower energies. So at n equals 2, we have 4 orbitals. Okay, because n equals 2, that means we can have a single 2s orbital and 3 2p orbitals. So then that means a total of 8 electrons. 3 2p's, that means times 2 per, that's 6, plus 2 from the single is a total of 8. When n equals 5, we have 5 subshells with orbitals. So we have one at the S, P, D, F, and G, which is not one we normally talk about. And we get a total of 25 orbitals. And since each orbital holds 2 electrons, that's a total of 50 electrons. And then C, just the number of orbitals in any shell n will equal n squared. And since there's up to 2 electrons in each orbital, the maximum number of electrons is 2 times n squared. All right, this table is probably, in my opinion, more important and a better example to go through. Doing these different calculations for atomic orbitals. So there's different parts filled in, and we have to find the missing parts. So to start off, we're told we have the 4f orbital. So that tells us that n equals 4. And f, so remember we have for L equals 0, 1, 2, 3 generally. And so F, that's SPDF. So L is 3. Okay, so the ML degeneracy, that's the number of orbitals in the L subshell. So that means we can have positive 3, start with negative. Negative 3, negative 2, negative 1, 0, 1, 2, 3. Positive, so there's a total of 7. And the number of radial nodes is n minus L minus 1. So that's 4 minus 3 minus 1, 0 nodes. So now going down to this next one, we're told n is 4, L is 1, and L at 1 is the p orbital, so this is 4p. And that since L is 1, that means we have negative 1, 0, positive 1. We have a degeneracy of 3. Radial nodes is equal to N4 minus L1 minus 1. That's 2. And then our next one, we have an N of 7, and we're given a degeneracy of 7. So if we have a degeneracy of 7, that means we have to have the F orbital, because that is negative 3, negative 2, negative 1, 0, 1, 2, 3. So that's a total of 7. And so that means we have an L of 3. And we have 7F. And we were also given a clue where we were given the radial nodes. So, and since we were told n, so we had 7 minus L minus 1 equals 3. Okay. So we have 6 minus L equals 3, negative L equals negative 3, L equals 3. So that was another way we could find L. And then lastly, we're given 5D, so n is 5. D, or the D corresponds to an L of 2. So our degeneracy, negative 2, negative 1, 0, positive 1, positive 2, we have 5. And our radial nodes, 5 minus 2 minus 1 is equal to 2. So I hope this somewhat made sense to you guys. I'll make sure there's some homework for you guys to practice with it. Again, come to me if you have questions on it, and there'll be a homework video on it next week, since it's not due for 2 weeks. And we're going to be building more on this with 6.4 and 6.5, which in my opinion are actually a little easier to understand. It's the workup to them that's the toughest part in my opinion. So Hopefully you're able to relax knowing that the hardest part is out of the way. And I hope you guys are staying safe, staying healthy, and I will see you soon.